The story of these strange lights in the sky began one night in 1973, when a U.S. Air Force pilot named Ronald Williams was surprised by an unusual sight.
There was a typhoon over the South China Sea. I happened to be flying over the typhoon. And as I was going right towards the center of the typhoon, there was a big thunderstorm just off the center of the typhoon. All of a sudden, just by accident, I was watching it, because if I'd have been doing anything else, I wouldn't have saw it.
Williams saw a bolt of lightning go straight up from the top of the clouds.
When it came up, I happened to be watching it, and I just watched it go up. I reported it, and nobody had believed me. They said lightning don't go straight up. Has a discharge on something.
But it turned out that Williams was not the only pilot to see lightning emerge from the top of a cloud and shoot upward toward space. As sightings accumulated, they became a part of aviation folklore, rare and unconfirmed events that hovered just outside the boundaries of real science. Until another chance sighting provided more evidence.
A fellow by the name of Jack Winkler had some detectors out. He was looking for something else, but he discovered them by accident with equipment that was operated on dark nights in Minnesota.
While testing a low-light video camera in 1989, Jack Winkler and a team at the University of Minnesota accidentally captured a black and white image that seemed to show the elusive upward lightning the pilots had described. Fittingly, this ethereal phenomenon became known as a sprite, a whimsical name that captures its fleeting nature. These giant pillars of light sparked an intensified interest in lightning and the dangers it presents to spacecraft during launch or landing.
Think satellite, you're thinking something the size of a car or bigger. It's the size of a loaf of bread, and that's our satellite. There's been some evidence that lightning produces gamma rays, and this is really the first satellite that's going to go out and investigate if and how and where and everything associated with gamma rays coming from lightning. There's been evidence, and others have seen this, but again, there's never been a satellite dedicated looking down at Earth for these terrestrial gamma ray bursts.
We want to make artificial signals similar to lightning and see what the board does, make sure it's filtering those signals the way we want.
We're going to put it into HDL code and then get it through this chip.
One of the tenets of the CubeSat program is to involve undergraduate students at all levels, from design to building to some of the theory, data acquisition, every aspect of this. So we're really training here the next generation of space scientists, of satellite engineers. As soon as the launch goes up and they know they're a part of that satellite and data's coming in, I mean, that'll be with them throughout their life.
Deep within their roiling clouds, thunderstorms hold an elusive surprise. Under just the right conditions, they produce some of the highest energy radiation naturally found on Earth, terrestrial gamma-ray flashes, or TGFs for short. Studies by NASA's Fermi Gamma Ray Space Telescope have shown that TGFs fire up about 1,100 times a day. Now, new research combines Fermi detections with ground-based radar and lightning location data. These studies show that TGFs come from more diverse types of storms than previously thought. In a thunderstorm, collisions among rain and snow cause different parts of the cloud to develop positive and negative electrical charges. When the strength of the electric field overcomes the insulating properties of air in the thundercloud, a lightning flash occurs. Most lightning occurs entirely within the cloud and is called an intra-cloud flash. All lightning produces a strong and sudden change in the storm's electric field, but the upward portion of an intra-cloud flash sometimes sends a surge of electrons rushing toward the upper part of the storm. Reaching speeds nearly as fast as light, these accelerated electrons give off gamma rays when their paths are deflected by air molecules. Using global lightning location networks, scientists can determine a TGF position more accurately than with Fermi data alone. 24 localized TGFs occurred within areas covered by next-generation weather radar systems. This gives scientists the opportunity to begin studying the kinds of storms that produce TGFs. These slices of radar data capture different types of storms encompassing a wide range of updraft strengths. Even the weakest of them produced a TGF. Another finding, TGFs seem to occur in the same altitude range, between 7 and 9 miles high. Lightning can form at much lower altitudes, so there's every reason to think TGFs can too. But gamma rays from TGFs occurring deeper in the atmosphere are greatly weakened. They're too dim for Fermi to detect, which probably means the satellite is undercounting them. TGFs may be far more common than we think. With this knowledge, scientists can design experiments to track storms and study how TGFs relate to their strength in evolution. This will give us an even better understanding of planet Earth's most powerful natural particle accelerator.
This is a very simple and basic structure of an electric motor. We can see the battery, the commutator, the brushes, the copper wire loop, and the permanent magnet. The brushes are attached to a wooden support, and the commutator is fixed to the loop of copper wire. The commutator rotates freely, rubbing against the brushes. Now, when we pass current through the circuit, this creates a magnetic field around the wire, which interacts with the field of the permanent magnet to produce a rotation of the loop that looks like this. The electric motor and the electric generator are related like two sides of a coin. In general, the task of an electric motor is to convert electrical current into mechanical force. On the other hand, an electrical generator converts mechanical force into electrical current. So as you can see, we can simply rearrange our motor into a generator. In this case, we will provide the mechanical force with a windmill rotor attached to the loop and connect a bulb in place of the battery. We will leave the magnetic field as it is, and as the wind rotates the blade, an electrical current is produced.